Hi, let's present another tutorial, this time about counter modulo 16, uh, something that has this kind of symbol that you see here, and it's going to be about the name of this device is going to be a counter modulo 16, like that, right? The objective is to invent a 4-bit presettable synchronous universal, which means up-down, binary counter, which may be an industry standard type like the 74169. And as usual, we will try to follow strictly the VHDL design flow that we have in mind all the time, from conception to the final prototype, with the idea of fitting the circuit in a programmable logic device type complex PLD or FPGA, right? This is the idea here. So what goes next, is the full sequence of the design flow: specify, plan, develop, functional simulation, gate level simulation, and timing analyzer testing, so that you get the maximum frequency of operation for a given target chip, and finally experimentation in a prototyping board. So the first thing to have in mind is the specifications, right? And here is when you have to talk about the symbol. You can review the commercial chip example, and you have to rename probably from the commercial chip. You have to imagine what kind of naming convention to use for signals. And then let's use all the time the same signal names. So let's make this new chip to resemble pretty much the other ones that we have studied before. And then we will talk about the function table, and finally the timing diagram, right? So that's the idea here, in order to specify completely the chip on the design. Hi, let me present you the idea of this kind of universal binary counter, right? Something that has to be specified by means of a symbol and by means of a function table, and something else like is going to be established later as a timing diagram example. Okay, so how the circuit is going to work? Well, you have the symbol that has several outputs and inputs, and for example you can recognize very well the typical inputs here, the ones that we name the clock, a kind of a signal that is going to be 1010 in some periodic pattern, and this is the clock period, which is equivalent to 1 over the frequency of the clock. And it's the same thing, for example, 200 Hz or 5 milliseconds. That's the clock period by which the counter is going to go ticking, right? That's the idea. Then you've got the clear direct as well. You know very well which is the use of this signal. It is called asynchronous, okay, reset. Asynchronous reset, because what is going to happen when you assert this signal is that the Q is going to go to 0 immediately. That's the idea of the asynchronous reset. Whatever you are, doesn't matter the state in which you are, you go straight to 0. And then there are some control signals, like the up and down, the count enable, that you know very well from previous examples of counters. And now you've got here a new one, which is called load. And what are you going to do here? You were going to load the parallel data input to the queue when you've got the right clock, okay, the right clock's rising edge. So that's the symbol with respect to the many inputs that you've got here. And then you've got outputs. For example, the code, the binary code, that is clear. Binary sequential. That's the code that you are going to have here this time, binary sequential. So the counter is going to be named like this: counter mod, from modulo, counter modulo 2 raised to the power n. And that n may be 4, 8, or 22, doesn't matter. It's just a parameter. It's going to be adjustable to the given number of bits that you like to go counting up. So, and then finally, you've got the terminal count that you are going to name accordingly, just to give a meaning to the modulo, right? For example, TC and then a number, 2 raised to the power n, to remember that, for example, TC 2 raised to the power 4, you know, the 2 raised to the power 4 just is 16. So, for example, this may be very well TC 16, terminal count 16, okay? So, good. If you know the symbol of this universal binary counter, now what is of interest is the way it's going to work, and that is reflected very well in the function table. On the left, you simply write the control signals, the ones that are going to be sampled at the risings, at the clock's rising edge, okay? So in this case, the load, the count enable, and the up and down. And what are you going to predict here is what is going to happen in the future. And you know that you represent that by Q plus. And this plus is nothing but the clock's rising edge. So the future here is very simple. Every time that you've got a rising edge from the clock, that's when you have a new number. So how is it going to work? Well, first of all, is this new and with priority, it has it is the signal that has more priority here, and this is the load, right? The load, which means that when you are asserting this line to 1, you know, doesn't matter whatever else you've got in the other control signals, because what you like to do, you see here very well in the table, is to photocopy, you know, data in is copied straight to the queue. And that is what the people call parallel load, because the data in is copied to the queue. And in this way, you can, if you are liking to use the counter in this way only, you know, because you can think here that you can enable and disable, and you can go enabling and disabling the load. So you can imagine the symbol in a simplified form. For example, n bit, okay, n bit for the data in, and then another time n bit for the queue outputs. So you can imagine a block like this that is controlled by the clock signal as usual, and then, you know, it is controlled by the clear direct as well, in case you like to clear the outputs, and then, you know, the load signal. So load may be 1 or 0. So this is what everybody call this data register, you know, data register, and this time n, and n to be 4, 8 or 64. Just what are you going to do is to sample the data to the right time when you've got a rising edge in the clock. So you sample the data, and this data is saved the queue, whatever it is, the combination of ones and zeros. So this is a data register of n bits, and normally it's going to be later when we go developing this, and it's going to be a file, BHDL file, because you simply have to use a simple file to do that job of data registering. So this counter works exactly as the data register if you allow it, you know, if you control the load signal, you can parallel load the data in, or you can do nothing, you see. For example, if load happens to be 0, so no active, and count enable is 0, you are not going to go anywhere. So the value of up and down has no meaning, because you are going to do nothing, right? The value is going to be kept. I mean, for example, 1, 2, 3, 4, counting up, and then 4, 5, 6, 6, 6, 6. You are going to go repeating the 6, because you are not going to allow the system count anymore, because the count enable is not set, right? So this is another way to go. And another one, and the typical one, and this is because it's a counter, normally you will allow the counter go up and go down, okay? So this is what you are representing here by, 1 in up and down. If up and down happens to be 1, the Q plus is going to be the current value plus 1. Arithmetically, if you have the number 12, the next one is going to be the 13. In modulo, for example, 16. This means that after the 15 you have the 0, and that way all the time. Or instead, if you like, you can go down, because this is where you have set here in the up and down L. So a 0 means down, So the next value for the counter is going to be Q minus 1 arithmetically. So after the 1 is going to be the 0, and after the 0, because you are going downwards, is going to be again the 15, and then the 14th, and so on. So up, down, do nothing, and parallel load. Okay, and remember that those ones here in the control signals are precisely the values that are sampled for these signals at the clock's rising edge. That's very important, because these signals may vary, they have different values in between the period, but the value that you are sampling at this rising edge is the one that is going to control the counter for another period of time. That's the way it works. And finally, the other signal of interest is precisely TC16, for example, or TC32 or 64. This means that this signal works in this way. When this signal is going to be 1 or 0 naturally, but it's going to be 1 only in these specific conditions. When you are not loading or anything like this, so working as a counter, but with a counter enabled. If the counter is enabled, right? If the counter is enabled, okay? So this is really like that. If the counter is enabled and you are in the last state, for example the state 15, 16 minus 1, if you are in the last state and you are counting up, okay, if this is what you do, this TC16 is going to be 1, or because you can work upwards and downwards, if you are at the last state when going downwards, Q equals 0, because you go 2, 1, 0, and then 15. So 0, it becomes the last state when counting down. So when counting down, up and down L is 0, and you are precisely in this state, the last state, which is 0, you have again another 1 in TC16. Else, 0, right? In any other state or in any other circumstance, for example, when counter enable is 0, if the counter is stopped, even if it is the state 15 and counting up, but you are not allowing the system go upwards or nowhere, so the system will have a TC16 equals 0. This signal, the TC16, it's connected to the counter enable of the next, right? So in this way you are generating a kind of a chain of counters when working towards a larger counter using this device as a component. So you can generate a chain of counters when working in plan C2, inventions. So you are inventing, for example, a counter of 48 using this kind of device. You can use 2 of them, okay, and you can go connecting them like these. TC16 of one of them is going to be connected to the counter enable to the next, and we will talk about that another time. So now it is just the idea, right? Why you like to have these poles in the end of the counting sequence. So this is almost everything from the specifications, exceptuating the timing line that goes next, right? So the next video is going to be for explaining how to build, kind of a sequence of different states in this way, in time. Okay, so that's more or less the way to go through this block, a counter, which you see at the same time is universal, can count up, can count down, and it is also a data register if you like to do that, okay? Making the corresponding connections, which is up and down connected to, doesn't matter, but if you connect count enable to 0 in this circuit, and you consider the load the control signal, then you've got another block which is perfectly right to call it data register 16 or 32 or 4. That depends on the number of bits that you've got here, right? So that's all for now. So if we like to go now and talking about the timing diagram, you see, okay, the timing diagram of this device, the counter modulo 16, for example, you have to do as usual, represent several, or 10, 12, 20 pulses from the clock, and then you can continue down here representing the initial pulse in clear direct, and then you have to go inventing values for load and data in and the other control signals. So you can see in a picture, which is pretty much a sheet of paper, the several ways in which this counter works. For example, this may be the load, then the data in, then the count enable, you have to go to the end, and then the the up and down, another input. So this is what you do normally, right? Represent all the signals in time, all the signals of interest, because those values here are going to be sampled. For example, you better like to do that first. For example, load here, and this is the data in, right? For example. So then, once the inputs are set here, you can imagine, or you can represent in time, the value that are going to be here for the several outputs. One of the outputs is TC16, for example. Another output that you can represent very well is the Q, right? So this is going to be the counter, the Q in time. All right? So let's imagine something. For example, how to start. And you know that in order to start a diagram like this, you have to take another pen and try to figure out when the system is going to go advancing, and naturally this is going to happen on the rising edges, and that one is the first. Okay, so that is your time now. You have to go this way, okay, representing the vertical lines. That means different time intervals, and they are going to be synchronized to the rising edge of the clock, that way. Okay, so you can have several of them, and now you have to go to the end, but that's the way. And now you have to start imagining how the system is going to be initialized. Okay, all right, so let's see. Okay, this is going to be the clear direct pulse. So now you know that from this period in time, from this time when you are asserting precisely the clear direct to be 1 here, at this time everything has to be known, because before this time neither TC16 or Q was known. It is not defined, okay? In this situation is not defined. Not defined, okay? But now, from now on, TC16 happens to be 0 and Q happens to be the value 0 in binary. For example, 0, 0, 0, 0, right? This is 0, 0, 0, 0. This is the initial state. And this is up to this point, but now you have to wait up to this point in time when there is a rising edge, okay? Here. So now is the time in which you are going to go sampling the data in and the load and all the inputs to see what to do next, because now the system is at 0, okay? So now it's time for you to imagine a kind of driving signals for data in, whatever the value. For example, here you are, well, 7, and this is, here you like to change to 14, for example. Why not? So you have 7 and 14, that's it, okay? And for example, here you are going to change to 2, okay? When you like, right? That's the point. This is your data, so you are going to change the data when necessary. So this is the data. Some examples of data in. 14, you know, 1, 1, 1, 0, 0, 1, 1, 1 for the 7, or 0, 0, 1, 0 for the 2, and so on. So this is the data that can be represented, any value of interest. Then load. So let's imagine that first of all you do nothing, okay, but later you drive the load for a while, and then you reset the load signal. So the load is going to be a pulse, and there is going to be a rising edge when this load is going to be sampled. Then count enable. For example, let's count enable, and then let's stop for a while, and then let's count enable again, something like this. You have to, and then up and down. For example, up all the time, and then, you know, later on down counting to see if you like to visualize another situation respecting the down counting idea, okay? So now with these signals you can start imagining how this is going to be. For example, the system is at 0, 0, you see. So now it's time for, there is no anymore a clear direct to consider. So now here is time for sampling the control signals. You sample a 0, so now you sample a 1, and here you sample a 1. So this means that accordingly to the table, the function table, you are not going to load, so the data in is no interest, and you are going to allow the system counting and counting up precisely. So this means that now the Q is going to be 1, because it was at 0, so now it's going to be 1, right? Then what? Another time for sampling, the same value, 0, 1, and 1, so you can repeat that, you see, up to 4 times. So for 4 periods of time, 1, 2, 3, 4, you have the normal up sequence. So the output is going to be like this, you see, 0, 1, 2, and 3, and then 4. Okay, so the system is counting up, 0, 1, 0, 0, that's the 4. Counting up, so you can name that that way. Counting up words, you know, counting up, that's what you can write here. Then what? Then it happens just at this new rising edge that you simply are sampling a 1 load. So it doesn't matter, you see, I'm not going to annotate now the count enable or up and down. I can do that, but it's not necessary, because accordingly to the function table, they are not going to be taken into account, the value of count enable and up and down. So if load is 1, the value that you've got here, which is 14, is going to be copied down there, right? So the system will jump from 4 to 14. So now, at least for one period, you have the number 14. And now is when you have to go ticking like these extra vertical lines for considering more situations in which you have to establish how the system is going to work, something like this, right? So let's figure out now what is going to happen. That you've been sampling the data in, which was 14, and now is registered at the queue. You see, you registered the data to the queue. So what goes next is a repetition, I see. So what goes now here is another 1. So this 1 means that the 14, because it's the same value, you see, you've got exactly the same value. This value is again copied down here, right? Okay, here. So now for another period of time, another complete period of time, you've got the same number because the data is the same 14. If the data had changed here in the middle of the period, you will be able to sample another value, but now it's the same. Then what? You continue this way without no loading data directly. So now again you have to see what happens in the counter. So the counter is 1 and 1, and then 0, you sample 0 and 1. So what is going to happen now? Well, 14, okay, and so this is going to be 15. Counting up, you see this is parallel load. Alright, this is parallel load, and now you have again counting up. So after the 14 it goes to 15. And now, you know, if you pay attention to the CC16, because you've got the system counting, if you let the system count, okay, and you are counting up, and it happens that you are at 15, you see, be careful, because now up to this point, you see what happens here? Up to this point, the TC16 goes high, but then it goes down because you do not allow the system count anymore. You see, it's a kind of an asynchronous output. It is changing. You see what happens here? Okay? Because count enable goes down, the TC16 pulse is less than 1 clock, because it has happened, this thing here, this is specific thing, that so you have to advance to the solution of the problem like this. Then what else? Then there is a new thing here. You do not allow the system count. Again, you see, you are sampling another 0. So this is not important, because again you've got 15 for another period, you see, so the 15 is just another period long. And what about the TC16? It is 15, but because you are not letting the system count, you see, this 15 is kept, and this pulse is not longer than this, it is less than 1 clock. And then the same and the same, so you can change that sooner, you know, if you like. You can change that here, for example, okay, and from now on you are going to let the system count, okay. So now, for example, you're sampling here 0, 0, 0, right? You are not loading anything, but you are having here another time you get a 1, right? So if you get a 1 and you are counting up, now you've got, instead of 15, okay, look at this, because it is interesting to see. This is 15 yet, because you have 0, 1, 0, 1, 0, you see, it is do nothing, you see, do nothing, the system do not move anywhere up to this point. Then now it is sampled again 1 and 1, so this means that instead of 15 you are going to have a 0, right? Now, but look at this, think about TC16, it is 15 and you are letting the system count up from now, from here, right, for example. So from now on, from when it goes high, from when count enable goes high again, you have this idea, and this mini pulse is generated because then you've got a 0, and because it's a 0, the next state, there is no need to represent TC16 anymore. So that's the way it works, okay? Then, for example, you can change the situation. For example, it's good for to be Well, let's try what happens with a change of up and down. For example, here you have different values, so now it's your turn to mark more vertical lines. For example, here and here and here and here another clock, so you are practically finishing the timing diagram. So let's analyze now another situation. This is another time, for example, sampling 0 in load, so acting as a counter, another time 1 and another time 1, so the system is going to be counting when this is another time 1 and this is another time 1 and then it's a 0, right, for example. So what is going to happen? You have 0 and then you have 1 and you have 2, but now, you know, because you are going to let the system count again and you are not loading data, but it is counting down, you have such a thing as a 1, so this is what you can call down counting mode of operation, right? Down counting, because now it is 2, 1, and another period is going to be 0, 1, 0 again, so now it's going to be 0, right? And because it's 0 and you are down counting, TC16 happens to be 1. Do you see the point? So now, if you like, you can simulate again how to load data. For example, this is the 2, okay? So this is the 2 here, the data in to the end. Or let's make it different. For example, the 8. Okay, this is the 8 from now on. And now, at this point, I will load, okay? So finally, I will need just a couple more clocks, okay, like this. So now what? Let's go finishing this. You see, you are sampling 0 here, and you're sampling 1, and you're sampling 0. So this means that 0, you have the 15 value, right? Because it goes down, and the next value to count is the 15. And then another time, no, because there is going to be a 1 here, and a 1 here copies the 8 that is here down there. So now it goes down to 8, okay? And then imagine that the data changes here. Precisely now it goes from 8 to 2, for example, here in the middle of the period or somewhere, you changes to the number 2. So what is going to happen now? That this time you have another 1 in load, so because you have another 1, the 2 is going to be captured again. So in the end, you see, at this point in time, you're going to switch from 8 to 2, and so there is no more terminal counts, and there is practically the end of the, you see, because you have a 1 in the load, there is no need to consider what is going to be count enable and up and down. So this is a kind of a practical thing. This is a kind of a timing diagram example, just imagining some values in the data in and the load, count enable and up and down, and trying to capture and predict which is going to be the corresponding outputs of the system, right? The TC16 and the Q in time from the very beginning, when they were not initialized to anything and they were not defined or not known. So you have to do that kind of initial pulse. You can have more pulses like this anytime you like, so the system will restart very fast, asynchronously, independently of the clock. And once you have initialized the system, you simply have to go imagining that you are this way, rising edge by rising edge, sampling the values in the control signals and calculating what is expected in the Q and TC16. So this is another timing diagram that has to be like that. You know, even if you see the picture of this now in the unit, this is nothing but, you know, It is a video recording because it's good to see how to start and how to continue and what is exactly what you have to watch in order to be able to determine the outputs, okay? So that's the recording. Thank you.